Hi there, my name's Cameron Lowe. I'm a field applications engineer with Tektronix, and today we're going to be discussing challenges faced in the double pulse testing environment, especially centered around wide bandgap topologies like silicon carbide and gallium nitride, and how Tektronix solutions attempt to overcome those challenges. So first, let's focus on why we're here. First, we have lots of different industries as the electrification in the automotive market has expanded into the electrification of just about anything. Whether we're talking about large battery backup systems for houses and commercial environments, to power systems for data centers that are focused on especially the power integrity that they are delivering to those centers, to MilGov environments who are focusing on electric vehicles not just from an efficiency standpoint, but from a focus on delivering quiet motor operation in those types of missions. There's wide bandgap topology everywhere, and the challenges in testing it are numerous. Okay, so when we're talking about double pulse testing, what are we referring to? Double pulse testing is not a new test. It's been around for many, many decades, but it's had sort of a resurgence in the development of wide bandgap type of topologies and high-powered IGBT modules. In the setup of double pulse, typically you have a half bridge of FETs or IGBTs, like you can see in this particular example, that are coupled together with a inductive load. In this case, since we're evaluating the low side FET, the high side FET is shorted, or in this case, there's a negative current on the gate, negative voltage on the gate that's attempting to hold it closed, and the load inductor is attached across the high side FET. Then we have a power supply voltage for VDS. Typically, a power supply is used also as a part of the gate drive circuitry. And the general sense of what we call double pulse testing is two different pulses that are injected into the low side FET's gate. And the intention is to use the first pulse to charge up the load inductor to its desired state. There's a brief period of dead time where the low side FET is turned off and the high side FET goes into sort of a freewheeling operation mode with the body diode included in it. And then the third step is when the pulse turns back on, or the second pulse is injected into the low side gate, at which point the FET turns back on. Some of the current that was freewheeling in the body diode and load inductor on the high side FET is then shot through, where you have a fairly significant jolt in current. And so the goal of double pulse testing is to vary the loading conditions, the dead time between pulses, the length of pulses, such that you're evaluating the switching mechanism of the low side FET, while also evaluating the energy that's lost during these turn on and turn off stages. And this can help plan for EMI ringing type of mitigation techniques, and it can also help in planning for the energy dissipation and heat dissipation that's going to be required within a power supply system. This slide is intended to show that while traditionally double pulse testing is done on the low side FET, there are certain circumstances where high side FET evaluation is done, at which point the load inductor is attached to the low side FET instead. There are different reasons for doing this. Generally, the reason for evaluating the high side FET is purely to evaluate the symmetry between the components and PCB traces and other parasitics between high side and low side characteristics. High side evaluation presents its own challenges, especially in making high side gate measurements. And a little later in the presentation, we'll talk about how to measure a high side gate signal in the presence of a huge amount of common mode interference. So why do we perform double pulse testing? Well, for a variety of different reasons. It's the general reason for performing double pulse testing is it's a very static single shot type of test that allows you to evaluate the switching transients and power losses that occur during switching events like turning the FET on and off, for example. There are all sorts of simulation tools out there that allow you to do this, but when incorporating these types of devices into a real-world PCB type of layout with all of the included parasitics that cannot be included in simulation tools, double pulse test is a good way for comparing those simulated results with real-world experimental results. We can also then stress the device in, again, a single shot type of scenario. So we can evaluate, what type of stresses, both from a heat and a power dissipation and ringing and EMI and all sorts of other different transient type of characteristics. We can evaluate those in a single shot characteristic that allows us to vary different components and specifications to fully characterize the device as a part of our real world subsystem or system level analysis. And then finally, we can also characterize this switching loss over a variety of different operating conditions. Those can include different external or ambient temperature changes, different loading transitions or different loading conditions. So double pulse testing, in short, is a very simple way to be able to evaluate lots of different characteristics and evaluate the switching losses of a half bridge or a full bridge type of system in a way that it can be characterized over a variety of different environmental conditions. Now let's talk about some of the challenges that are faced when making double pulse measurements. One of which is related to gating different measurements. So the example I'm showing here is one of the many measurements done during double pulse testing. This is calculating the energy dissipated during the on and off periods of the FET. So here you can see VDS going low, ID going high, and you can see an energy on and energy off state. And the energy that is calculated during this event is the result of usually a math waveform trace that multiplies VDS times ID to get power, and then an integral across a specific time period in order to calculate energy. Now that seems very simple, but this time period calculation is done in very specific moments. So there are different standards from the JEDEC and IEC communities that specify where this energy on and off characteristic needs to be measured. Generally, we're looking for the 10% rise point of IDS and the 10% fall point of VDS when it comes to the energy on losses. Now, that gating can usually be done with cursors as an example. So you can put cursors on either side of where that 10% point for VDS and IDS is. But since this measurement can vary by pulse width, those timing characteristics, those changes even a small amount in skew, or the changes in loading characteristics of IDS, for example, might throw off your cursors. And so that requires you to then move those around every single acquisition. So what I'll show a little later is that we have some advanced software running on our oscilloscopes that performs this gating characteristic for you and then shows you where that gated measurement exists. Similarly, there's a type of measurement called diode reverse recovery characterization. And again, this is measuring the response of the high side body diode of the high side FET and its ability to recover from when that second pulse turns back on. So as I mentioned in the scheme of double pulses, when the low side FET is turned back on a second time, there is a small amount of current that is rippled in from the body diode in a sort of a shoot-through effect. And so there are different measurements that are performed there. One is the magnitude of reverse recovery current, some of which is the current discharge rate. And finally, one that's highlighted in blue here is what we call the recovery softness factor, where we actually are measuring the tangential line of this recovery current as it attempts to shoot back to zero. And that includes, the dissipation effect, the rate of effect as it comes back to zero, and any sort of ringing that might occur during that event. So all of this is apparently is discharged and characterized. And again, the same sort of principles apply here as we showed earlier. There's a gating factor, especially for this charge type of measurement, where again we're making an area under the curve type of analysis. And so gating that measurement can be challenging in a couple of respects. And again, we have some software that allows you to do this measurement more easily. Another challenge, again, when talking about high side double pulse measurements, is the effect of common mode interference and the ability for differential probes to reject that common mode interference. So, as you probably know, there are high voltage differential probes out in existence that have lots of differential voltage range. But generally speaking, traditional differential probes have a challenge with what's called common mode rejection. This is the ability for the differential amplifier in a probe to reject voltage that is presented to both the plus and minus input. And so what we'll see is one of our differential probes that we would normally use in this environment has pretty decent common mode rejection, maybe 80 dB or so. But once you start getting out to hundreds of megahertz, which again is a bigger challenge in wide bandgap devices nowadays that are switching faster and have a faster dB/dt, is the challenge there is that the common mode rejection ratio in that particular state is much lower. So I took an example here where we're looking at a typical, let's say 1200 volt silicon carbide module as an example. And we're looking at the VDS voltage, which in most cases is 20 to 25 volts. And so when we're measuring that gate voltage in the presence of a bus voltage on the high side FET, so again, not ground referenced, the common mode error that is presented is roughly 60 volts. So you can imagine viewing a signal of 20 volts in the presence of 60 volts of error presents lots of challenges. And we'll show exactly what that looks like here in a second. Our solution to that is using what's called an isolated differential probe. In this case, our probe here has 5 fiber optic cables that go between the probe head and the compensation box back on the scope connection. And those fiber optic cables galvanically isolate the probe head from the scope. And the result of that galvanic isolation is a huge amount of common mode rejection. So here we have 100 dB of common mode rejection at 100 hertz. And so the resulting common mode error now is, you can see, significantly less. We also make use of MMCX style connections, which are great kind of barrel style connections that shield out external noise and EMI and other common mode interference type of signals. And they're also a very robust type of connection that you can sort of seat in and out of different test points around your board. So let's take a quick example of where this common mode interference comes into play. So here we've got an example where we're looking at in this case, a gallium nitride FET with a gate voltage of 5 volts, a bus voltage of 50 volts. And we're going to compare the result of our isolated differential probe versus kind of the more traditional 200 megahertz high voltage diff probe. So here's an example of a screenshot that was captured, and here we're looking at the high side FET turning off. So you can see the green trace and the red trace are identical in the circuit. So they are the high side VGS waveforms, and the orange trace here is showing the low side gate. So here you can see high side gate going low and low side gate coming on, and the ringing that is presented in that red trace, especially in this particular area, is significant enough to where it appears at least that the high side gate exceeds the voltage threshold, at least for a brief period of time, at the same time that the low side gate is going high. So you would expect at least a small amount of shoot through. And so the result of that kind of information would be either a drastic reduction in duty cycle between the high side and low side gate, or increased dead time between those two pulses. But all of this ringing is presented as a result of that common mode interference. So this ringing is not actually real. It is the result of the measurement error from the load common mode rejection of that particular probe at extremely high frequencies. The real common mode interference is just this small bump that we see down in the green trace, which again is what we would expect. It's there, it's available from the switch node itself, but it's not nearly to the magnitude that we would have to worry about any sort of interference or coupling through towards the voltage threshold of the high side FET. So this is one example where common mode interference kind of muddles the results of your gate drive analysis, and where an isolated differential probe makes a huge significant difference. Current probe options. So current measurements in double pulse testing are also challenges, and so what I thought I'd highlight is various options that exist out in the market. You can see they all have advantages and disadvantages. I would say by far the most common way for measuring current in the market today, at least, is generally Rogowski coils. The reason for that is they're fairly inexpensive. They have a pretty significant current maximums to them, and the Rogowski coil allows you to wrap around different parts of the coaxial cables that might be used, or easily access and change test points around fairly easily. Their challenges, though, are that they generally are limited in bandwidth, and so as we switch currents faster and faster, we're going to reduce the rise and fall time and kind of muddle over what could be additional losses that we're missing. They're AC only, so they don't capture any sort of DC offset that might exist, and they, of course, introduce an additional loop that needs to be accounted for. Coaxial shunts are becoming more and more common. They add additional benefit of increasing the bandwidth to capture those additional ringing pieces that are normally muddled out in double pulse testing. But of course, given their design, they obviously add in additional resistance that has to be accounted for, additional inductance, and depending on how your board is laid out, they can be a little bit bulky to have access to. So again, there are lots of, as with anything with oscilloscope probing, there are advantages and disadvantages, and these are highlighting some of those on this particular slide. This is one example where we see a difference in some of the losses when comparing the results captured by a Rogowski coil and a current viewing resistor or a shunt resistor. So here you can see the additional blue trace that shows up over here. If you were to integrate under that curve, you would capture additional loss across this area that is normally left out, again, because the Rogowski coil's reduction in bandwidth mitigates some of that loss or rolls it off in sort of a low-pass filtering effect. In response to some of the challenges with existing current probe solutions, Tektronix has also now just recently released a new isolated current shunt probe. We're calling it our TICP. And what's unique about this particular probe is a couple of things. It introduces an RF isolation between the probe tip and the connection point back at the oscilloscope. That provides excellent common mode rejection and provides a level of safety as well to the end users in using that RF isolation between those 2 points. The shunt solution also enables the user to connect down to their existing shunt, usually a coaxial shunt, on the circuit board. The probe tips themselves of this particular probe are designed mostly for MMCX style connections, which is a heavily shielded coaxial RF style connection. And when attaching down to a current shunt, we can achieve either very low levels of amperage in terms of measurement, or again, depending on the current shunt that's being used, very high levels of current. So with one particular probe, you can swap out different current shunts being used and fit the needs of whatever you're trying to measure. Also, the one more benefit is that we add these tips to have extremely flexible connection points. This gives the user an endpoint to really ensure that the strain of a connection point or the movement of the probe is going to be balanced between the strain that might be applied back to the probe or to the test point down on the board itself. So I'd encourage you to check out our new TICP probe. It's designed specifically with some of the challenges previously mentioned in terms of achieving a wide range of current with a wide bandwidth range, all in a very user-friendly current shunt configuration. Okay, one of the last challenges we'll talk about here is gate drive control. So, of course, for double pulse testing, it's required that you generate two different pulses of varying lengths, and that's not easily done with older function generators out there. In most cases, I find customers are doing this with some of the microcontrollers that they're using as a part of the motor drive systems or the gate drive controllers that they might already have on their circuit board. But just to mention, we do have a very easy and simple solution to use for that double pulse generation, and that's our AFG 31000. This is a really inexpensive function generator that allows you to generate two different pulses, either with a on-instrument GUI that allows you to adjust the dead time and pulse width accordingly, or as I'll show you here in a second, we can network connect into the AFG from our scope and operate it completely out of the scope's user interface. So for those that don't have a gate drive circuitry capable of generating double pulse testing, the AFG 31000 is a great solution. Okay, let's jump into a quick demonstration to show you what our double pulse testing capability looks like. Okay, the demo device that we're going to be showcasing today is an evaluation board from ST Micro. It's using some TO220 style silicon carbide FETs, and you can see the box over here on the right-hand side has some very easy kind of banana receptacles to probe into using our differential probes and our split core current probes. Those are all attached back to our MSO6 series. And we also have the function generator I mentioned, the 31000, coupled in here showing off its double pulse GUI operation, and a triple output power supply from our Keithley product portfolio that's generating 25 volts for the VDS voltage and 5 volts for the gate drive circuitry. Okay, now moving to the oscilloscope screen, I'll describe kind of the setup here, and then we'll start capturing some results. So on the oscilloscope, we have channel 1 dedicated to capturing VDS. We have channel 2 capturing the current flowing through the low side FET. And we have VGS captured on channel 3. And then we'll see a math waveform trace that captures the power dissipated during the switching events, or VDS times ID. What we do to set up this measurement is we go into our measurement analysis tool. We select wide bandgap double pulse test, which is a software option you can add to our oscilloscope for double pulse testing specifically. Here you'll see a wide variety of different measurements from our switching parameter analysis, which captures energy on, energy off, the V peak and I peak. Switching timing analysis that gives you the time to turn on and time to turn off analysis, as well as dVdt and dIdt. The diode reverse recovery analysis, where again you can view the time that it takes to recover from that reverse recovery current, the charge that is dissipated, the reverse recovery softness factor. And then we also have a capacitive analysis that looks at the output charge, again dissipated during different events. So in this case, to set up this measurement, we're going to select energy on. We're going to adjust our voltage and current sources to align with what we have plugged in. And then we'll add that measurement over here on the side. Here we can plug in the expected maximums from a voltage, current, and gate voltage perspective. This, in combination with the pulse width that we've inputted, is going to allow us to easily auto set our scale both vertically and horizontally when we plug in and activate this circuit. I mentioned we can also control our double pulse generation externally using a LAN style connection. So I have my AFG connected on a LAN connection here. I have the high and low side voltages plugged in, the load switch to high Z. You can generate more than 2 pulses, but in this case we're generating a first pulse of 5 microseconds, a dead time of 3 microseconds, and then the second pulse is 2 microseconds. So once that's all plugged in, we can hit the power preset button to auto scale our setup, and then we can hit gate stimulus to actually generate those 2 pulses again from the external function generator, and then capture those results on the oscilloscope here. So I'll activate our supply voltages from our power supply. I'll hit our trigger button on the function generator, and now we've captured these 2 different pulses. So if we go to our oscilloscope screen, you can see VDS showing the off or the low state at which the low side fed is pulsed twice. You can see ID here rising to roughly an amp in load current turned off, and then this large spike here is a representative of the injection of that reverse recovery diode current. And then VDS times ID is showing you a very significant spike down here at the bottom. Now, if we want to zoom in on that, we can select the energy on state. We can select maximum here, and it will zoom in on this particular component. So let me drag VDS times ID on top of each other, and we can turn off our VGS voltage for a second. And you'll see in our math waveform trace indicating power, this dashed green cursor is showing the start and end time point for the gating of that particular measurement, which again lines up with the 10% point of ID and the 10% falling point of VDS. So this measurement now provides us with an analysis of roughly 3 microjoules of turn-on loss. Subsequently, we can get other measurements like energy on, energy off, our V peak, our I peak, our time to turn on and our time to turn off. And in this case, we're measuring the DIDT, showing roughly 50 amps per microsecond of a slew rate. So all of these measurements can be populated in a very simple average. If you were to have multiple pulses, this energy on and energy off and other measurements would all be averaged over the acquisition length. We can also pull up a results table of these measurements that allows us to see these measurements in sort of 2 different statistical methods. The methods shown over here on the right-hand side show mean, min, max, standard deviation, and population side for a single pulse or a single acquisition. But if we were to pulse this analysis several times, we can start to capture more than one such result. So note I can trigger our function generator several times here, and now we have 4 different acquisitions to then average out those results. So this would be a really useful tool if you were, for example, taking these measurements over an extended period of time to vary temperature, to vary loading conditions, other environmental kind of characteristics that might change in a rather slow time, and allow you to get more analysis in terms of what to expect from a switching analysis characterization over time. So with these results, we could take the energy on losses, the energy off losses, maybe the conduction losses across this switching time frame as well, multiply them by the switching frequency of our device in operation, and get our total loss profile that would then allow us to plan for the expected power dissipation and then come up with the appropriate heat sinks and other heat dissipation techniques to maintain our device over its operation. So in summary, our testing challenges with double pulse testing can be alleviated by utilizing a software package on our newer oscilloscopes that allows you to set up and characterize the measurement in a repeatable fashion, as well as a simple way to characterize the dynamic performance of your system over a variety of environmental conditions. If you'd like more information about our double pulse testing solution, we've got a number of different articles, application notes, video online demonstrations. Thanks very much for your time. If you have more questions about our double pulse test solution, you can feel free to email me at cameron.lowe@tektronix.com. Thanks.